Okay, so I will start with the indefinite integral or antiderivative. So we know what is antiderivative, right? So antiderivative is, suppose if you have a con- continuous function f, okay, let's say it's a function from some R to R. So an antiderivative of this function f, is a function g. It's a function. So, sir, let me call that capital F, such that the derivative of the capital F is nothing but the small f. Okay. So this is the antiderivative, and if such a function exists, then it is called the antiderivative of the small f. And sometimes people use the word integral, and this f is also written as integral of f dx. Okay. Okay, so we have seen some of the theorems that when such a antiderivative exists, and one of the thing is if you have a continuous function. So if you have f is continuous, uh, then the antiderivative exists. Okay. Uh, then integral f dx exists, and we also have seen how this integral is defined, right? So see, the integral can be defined in two ways. One is you do the mean value theorem. So you defined using the Riemann integral, and there is this concept of antiderivative, and the fundamental theorem of calculus gives the connection between the antiderivative and the Riemann integral. So basically, these are in some sense related. Okay. So the Riemann integral is basically something called a definite integral, where you have this bounds here. For antiderivative, you don't have bounds. But anyway, what we trying to do today in today's class is basically if you give a function, okay, so how do you find the antiderivative? So we will discuss a few rules which you might have done in your 12th standard, I think, if you took the math course. So we will just do that much, and then the new thing that we might do here is some numerical integration. Okay. So let's start with the rules of integration. So there are certain basic integral rules that one can easily find. So first I will write a few of those. See, I have a notes here, so I will just use that to write it, because it always a good idea. Because see, I was not very comfortable. I mean, usually I don't need notes, but whenever this calculation comes, I was not very happy with that, so I will have some take some notes. Okay. So you have, let's say, if you have an integral k dx, so this is nothing but kx dx. Sorry, kx plus c. Okay. So yeah, and I mean, I'm just writing few formulas. For example, if you have x power n dx, this is nothing but x power n plus 1 uh, by n plus 1 plus c. This is true for all n not equal to 1. And when n equal to 1, you have integral 1 by x dx. So this is nothing but the natural logarithm of mod x plus c. Okay. If your x is, if you only consider the positive direction, then you don't have to write the mod here. Well, I mean, you need mod anyway. So it's an indefinite integral. And if you look at the integral of e power x dx, this is nothing but e power x plus c. Okay. And if you look at the same thing, instead of e power x, if you change the e to any any positive real number a, and you consider a power x dx, this will be ln of, sorry, 1 by ln of a. Okay, a power x plus c. So this is true for all a greater than 0, and a has to be not equal to 1. Okay? Because 1 power x is 1, and this does not make sense. Okay. Okay, so these are some basic formulas, but we are just going to use this to get whatever we want. So, but just to give me 1 minute, I have to check something. Yeah. So, if you want, you can always write other formulas. Some trigonometry formulas are there, so you can just type some standard formulas. You can get it in the internet. So I am not going to write all of this. We will write only few, and then we directly go to the examples. So before that, I just want to write a few more rules. So if you have, let's say I write a theorem maybe. If you have integral k f of x dx, this can be written as k times integral f of x dx. Okay. And if you have integral f of x plus g of x plus or minus g of x dx, then this is nothing but integral f of x dx plus or minus integral g of x dx. Okay, depending on the if there's a plus here, here also the plus. If there's a minus, here also there's a minus. Okay, so these are the standard rules, and if you want to uh, see why this is true, basically what you do is you take the derivative of this, and you can see this two function has the same derivative. And if you have a two function which has the same derivative, they are differ by a constant. Okay, so of course this is a always differ by a constant here, where c is a real number. Okay, so that we have done in the last class. So if you have a two differentiable function f and g, such that its derivative is same. Okay, f dash is equal to g dash, then what we know is uh, f minus g is a constant. Okay, so this we have done in the last class, and you can try to prove it by yourself. It's not very hard to do it. Okay. Okay, so these are the few things we will start with, and then let's start trying some problems. So let's start with the easy ones, and then we go little higher at each step. Okay. So let's start with the first problem. And by the way, after this, I just want to mention one more thing. So these are some standard thing whichever I'm defining here, because I'm going to use all of this. So that's why I'm giving you. But there are other things one can write. So if you want, okay, let me ask a question. How do you prove? Let's say we take this. How do you prove that uh, the integral of this is basically this term? So we want to say that this is the antiderivative, right? So this is the antiderivative of this term, right? So x power n. So what you do is you take this term and take the derivative of this. If you take the derivative of this, what happens? This is n plus 1, okay, x power n divided by n plus 1 plus, see, the derivative of constant is 0, so you don't have to worry about that. So this will get cancelled, and whatever you get here is uh, x power n, right? See, that's okay. It's not x is not equal to 1. It's x is not equal to minus 1. Okay, n is not equal to minus 1, because when n is equal to minus 1, n plus 1 became 0. In that case, you cannot do the cancellation. So as long as n is not equal to minus 1, you can cancel it, and this term holds. Okay. So whenever I write these things, all to prove it, all you have to do is you take the terms and take the derivative. Okay, and then you do. And if it became whatever you have here, then the formula holds. Okay, so you can see in the assignment there are so many problems which might look hard. So some of the integration we will do by directly how to. So if I give a some complicated formula here, how do you get the integral? We will do here, but the thing is, in the assignments, if you want to solve it, one of the easy way to do is you take that thing and take the antiderivative, and if it becomes whatever you want, then you don't have to worry much about that. Okay, so that's one way to solve the assignments, but we will do little bit more here. Okay, so let's start with the easy example. So we integrate three. Okay, before going to the example, I just want to say one more thing. So this is about the indefinite integral. So definite integral means you will have limits here, limit a to b, f of x dx. Okay, so now you have an indefinite integral here, which is let me write indefinite integral f of x dx. Let me call this as capital F. And you have a definite integral here, which you can either see as a area under the curve, or it is defined in terms of the Riemann integral. The relation between this antiderivative and this definite integral is basically given by the fundamental theorem of calculus, which says that this is nothing but f of b minus f of a. Of course, you have a conditions like, let's say, f is a continuous function. Under certain hypothesis, this is true. Okay. So basically, that's why sometimes you want to compute the indefinite integral, so that whenever you want to compute the definite integral, it's basically you're substituting values here. Okay. So computing this is interesting because it helps you to compute any definite integral. Okay. But I just want to tell you, sometimes the antiderivative may not. Yeah, sometimes computing this is easy. This theorem only holds under a certain strong condition. It's not always true. So probably I'll just look at the condition. Just give me a minute. I mean, I'm just looking through the notes. I want to write the condition, but I don't want to make error. So just give me a minute here. Yeah. So yeah. So the question thing is, if f is a Riemann integral, then you have this. Yeah. So probably write it. I will write the statement properly instead of. So this is basically second fundamental theorem of calculus. So it's very useful statement. It says that if you have a f which be a real valued function, on, let's say, closed interval ab. Okay, and you have this capital F, which is continuous on the closed interval ab, and also that an ab, which is an antiderivative of f. Of f in open ab. So antiderivative means again just f prime of x is nothing but f of x. Okay. So these are the conditions on the antiderivative. Now you also have a condition on the function f. If your function f is Riemann integrable, Then what you have is integral a to b f of x dx. This is nothing but f of b minus f of a. Sorry, capital F of a. Okay. So the reason I was writing this, and I don't want to make any error, I just want to look at the notes and write it. Uh, is because this f is continuous is there, right? It is actually a very important condition, because there are times you have a function f, uh, and it may be remain integrable, but it does not necessarily have a antiderivative. Okay, so in that sense, having a continuous antiderivative is actually a strong condition. Okay, so we have done one example, right? Already we have done in the tutorial. If you remember, you take this step function here. Okay, so till 0, including 0, let's say it's minus 1. But after whenever x is positive, this function is 1. Okay, so you take this function. What we have shown already is that this function cannot have antiderivative. Okay, so basically what you can easily prove is, if you have any function, its derivative has the intermediate value property. So if you remember, uh, let's say f is a differentiable function on your closed interval ab. It's not closed interval, open interval ab. Uh, then what we can prove is, then f has a intermediate value property. Okay, you remember the intermediate value property, right? It's like the intermediate value theorem. So if you have a differential function, no, then the derivative has intermediate value property. So this is a way stronger. It tells you the derivative need not to be continuous. Even though the derivative is not continuous, it has the intermediate value property. So if you look at this function does not have an intermediate value property, because let's say if I take 0, there is no x in real number for which the f of x is 0, right? So this function does not have intermediate value property, and therefore this function cannot have antiderivative, right? But it has a integral. If you want to find, let's say, integral from minus 1 to 1, if you compute the integral, which is the area under this region, and you can clearly see the integral is 0. Okay, so what I want to emphasize is, this condition that the antiderivative exists and it is continuous is actually very important. Okay, under those conditions, you have this theorem which is very useful. So these are the preliminary thing that you want to know. Okay, so I just want to emphasize this is actually important. Okay, so let's move on to the problems, and we will start doing problems. There are few things I just want to tell you before we start the problem. I just want to tell why actually solving this indefinite integral is interesting. Okay, so let's start with the first problem here. You have integral 3x power 7 dx. So how do you integrate this? So this is the first problem. Okay, so if you want to integrate, what you do is you apply the first formula. You apply this theorem here. So where you have a constant, you can take the constant out. Okay, and then you have this formula, integral of x power n. You have formula. It is x power n plus 1 by n plus 1. Okay. So this will be, so you have to, you can take the 3 here, and this will become x power 7 dx. And now you can integrate this one. This will be 3 times x power 8 by 8. So this is on the plus c. Okay. Because indefinite integral can differ by a constant. Okay, so this is the easy example. So I will start a little slow, because if somebody does not have done uh, integration in your 11th or 12th, or if you doesn't do it properly, then I don't want to rush. We will start slowly and let's make it self-contained. Okay. So let's look at the second example, which is integral 1 by, let's say, root x dx. Okay. So how do you do this? So what you do is you do the same thing. You write the 1 by root x in the exponential form. This is x power minus 1 by 2 dx. Okay. And now what you do is this is again of the form x power n, right? And as long as n is not equal to 1, not equal to minus 1, we can use the formula. This will be x power minus 1 by 2 plus 1 by x power 1 by 2 plus 1. Okay. Sorry, not 1 by 2 plus 1. Minus 1 by 2 plus 1. Yeah. And this is, if you look, it is basically x power 1 by 2. And here, whatever you have, it is basically you will get 1 by 2 here. So divided by 1 by 2. But then that is nothing but 2 times x power 1 by 2 plus c. Okay. So you have this property, right? If you have a by b by c, then you will write it as a times so c by b. Okay.
So
Not it. Yeah.
we can solve the question number 2 by multiplying and dividing by 2 and using the antiderivative as well, no?
Multiplying and dividing by 2.
And then
Yeah,
one.
sure, sure, sure. Yeah, we will. Yeah, that is also true. So
All right, sir.
yeah, yeah, I will write that another method. Let's say. Okay. So basically, if you look right, that's how this formula came into picture. So whatever you have seen, right, that's a nice observation. That is exactly the formula comes, right? If you multiply and divide by that and do that, it basically you will get the entire formula here. Okay. So sometimes to find the antiderivative, it's basically you might have an intuition. Okay, this is how I want to do, and yeah, that's how you do it. Okay, so all these things are most of the time guesswork. I mean, at least the certain things, at least for let's say this one, you don't need to do much. It's basically guesswork, right? And this is also a guesswork because you know that if you take the derivative of the log x, you will get 1 by x. So some of these are guesswork, and you know that e power x, if you differentiate, nothing happens. Yeah. So what you said is also true. So you can basically multiply and divide by 2, and then you can see that that looks like uh, the antiderivative of x power 1 by 2, and then you can just simply do the trick. Yeah, yeah, that will also work. Okay. Let me move on to the third question here. Okay. So I'll just write simply, probably 2 steps I'll write here. I mean, again, we are going step by step here. Uh, because I think we have 2 hours, so we have enough time to proceed. I think. Okay. So let's do this one. Let's say 2x power 5 plus 8x cube uh, minus 3x plus 5 dx. Okay. So how do you do this? So what you're going to do is uh, first you apply the, it is a integration of a sum. Integration of sum is nothing but sum of integral, right? So this integral can be taken, distribute over the sum. So 2x power 5 plus integral 8x cube minus integral 3x plus integral 5 dx. Okay. So this is what you have. See, do I need to add a c here?
No, sir.
Why is that so?
Because we are just distributing the integral symbol and not performing the
Yeah.
integration.
Yes. 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 So what you are telling is by the statement it tells you that the antiderivative of this function is basically the antiderivative of this function. Okay, that's all we are doing here.
Yes, sir.
Okay. So then we take antiderivative in each step. It is x power 6 by 6 plus 8 times x power 4 by 4 minus 3 times x square by 2 plus 5 times x, right? And here you have to add a constant because not only this is the integral, uh, any constant if you add it, that is also an antiderivative. Okay, and you can simplify this one. Probably I will not simplify it, but I mean you just have to cancel few things which you can cancel, and then you will have it. No, I think did I write any made any error here? No, I don't made any error. But okay, let's do another problem here. So this one may be little bit harder. Not very hard. It is also easy only. 2x plus sorry minus 7. Let's say minus 7 by x. So how do you solve this?
We can distribute the x in all the three terms and
Yeah.
simplify.
Okay. Yeah. Okay. Cool. So I will do exactly what you said. We just distribute the x and then simplify. So this is basically x square by x will come, but x square by x is not, sorry x cube. Let me make it x cube for now. I mean, yeah, this is a problem I started, so I will do it. Yeah. So you just simplify. You will get x square plus 2 minus 7 by. If you got it. I mean, you can mute your mic maybe.
Oh, sorry.
Yeah. Thank you. I mean, because I'm just recording here. That's why I told. Okay. So we will continue here. So this will be the each time we integrate separately. So this will be x cube. See, this time I'm not going to write like this, and I think you it will be understood that this is what we are doing. So this is x cube by 3 plus 2x minus. Okay, now how do you do this? Here, let me write this time maybe 7 by x dx. Okay. So how do you do this? This you do.
We can take the 7 out and we know by the basic formula that integral of 1 by x dx is ln of x.
Yeah, exactly. So mod ln of x. That's all. Okay, and plus a constant. Okay, so basically, see, there are for many other functions. So if you don't remember it, probably you can just look here for a minute and probably try to recall it. We are just using this formula. And there are for the integral of sine x, cos x,
Sir,
everything is known, but I'm
sir,
not
in this
writing it here, so I'm
example,
not going to.
after dividing x square, yes, sir.
Yeah, yeah.
Sir,
Are
there
you
is
telling
something.
something?
Sir, there is something in first term after dividing x square by x. Sir, you write x square in this, sir.
For here?
Yes, sir.
Oh, oh
X
no,
cube
no,
by
no.
x.
Yeah, I
Yes,
made
sir.
a typo here. The
Okay.
problem is I have in my notes I wrote 3, but when I wrote it here I made a typo. I wrote it 2. I mean, it doesn't matter if you put a 2 here, then you will get a x here.
Okay, sir. Understood. Understood, sir.
Okay, okay. I mean, yeah, I just when I copied it, I made a typo. So I just yeah, I could have continued with whatever I had, but yeah, sorry about that. I should have continued it. But anyway, so let's proceed to the next type. So this much is not very hard, right? So let's let's just uh, increase the difficulty of the problem, and then we will proceed. Okay. So let's start with the problem, and then we will come back to what we can do. Okay, so now we have a problem like this: 2x plus 1, let's say, by let me write 2025 dx. Now, how do you solve this type of problem? So probably I will tell you the idea. I think somebody has said something. Yeah, substitution. So I will explain what you mean by substitution. So what you can do is somehow you try to see. Let's say I have this function here, okay, but let's say this is quite complicated. If I know something like uh, x power 2025, then I know how to integrate, right? So x power 2025 is nothing but x power 2026 by 2026. Okay, that I know, but now I have something here which is stopping me from doing that, right? So now what you do is you take this as let's say some u. So you take instead of this term, you substitute as u. Okay, this will be 2x plus 1. Okay, see there are two types of substitution, but right now I'll just do one type here. And I mean, I remember there is two type, but I didn't prepare. So I mean, I didn't prepare two type. Only when I say substitution here, I remember that one can do differently. Probably I will explain what is the two type, but I didn't prepare a problem, so I didn't want to try at the spot. But anyway, so here you see what kind of substitution you do. So you have this in idea, then I will come back and tell what is the other problem. Okay. Uh, so okay, so let's continue here. So what we did is instead of this term here, we put we substitute as u, right? Now then what happens is if you take du by dx, okay, because what is u? U is a function of x, right? So I can take du by dx. Du by dx is nothing but uh, 2, right? So du by dx is nothing but uh, yeah, d by dx is nothing but just 2, yeah, 2, and that gives you du is 2 dx. Right now, what happens is instead of this dx, you can substitute du by 2, and instead of this term, you can put u. Okay, so if you write here, this is u by 2, 2000, let's say 25 dx. So now you can take the 1 by 2 outside, and now you can integrate the way you want. It is 2026 by 2026. Okay. And plus c. And if you want, you can compute what is this term. U 2026 divided by, I think this is 4032. If I am correct, this is the term. Okay. So this is what we have, but probably I will tell you exactly what is the theorem says. Okay, so the theorem says the following. So because I'm doing something like I'm taking this dx to this side, right? I want us to make sense of, okay, what does this means? How do you take this to the other side? Okay, so the theorem, this is basically integration by substitution. I'm not going to give the proof. So the theorem is, if you have an integral f g of x, g prime of x dx, uh, this is nothing but integral f of u du. Okay, and you have the substitution u equal to g of x. Okay, so this is the theorem, whatever you have. So in some sense, you can see it like this. Okay, so this term, if you look at this term, you can see this term as f of g of x times d of g of x. You can see this integral as like this. Okay, and when you have so what basically you're doing is, instead of seeing uh, this function as a function of x, so you have f of g of x, right? Now you are seeing this as a composition of two functions. Basically what you're doing is we are trying to reverse the chain rule. Okay, so here you have f of g of x here. This is you are seeing it as a function of x. Instead of seeing it as a function of x, you can see f as a function of g of x. And when you see f as a function of g of x, then this is what you have. So it's in some sense we are trying to reverse the chain rule. Okay, so let's do some more interesting problems here.
Hello.
Yeah.
Sir, I remembered something from my last classes that if we have some standard formula of integration,
Uh,
and if x is substituted by the polynomial of format ax plus b,
okay.
then we can just integrate it by using the formula, standard formula,
Okay.
and then divide it by the coefficient of x.
Okay. And then.
Is it true?
Okay. Can you repeat again? Maybe I will write here and see.
Yes, sir. In a standard integration formula,
Okay. I mean, what you're telling is a standard integration formula, right?
uh, yes, like x to the power n or 1 by x, etc.
Okay. Let's say x to the power n. Huh.
So if we substitute the x
Okay.
by the polynomial of format ax plus b,
Okay. You want to substitute this as a x
yes,
plus b. So
yes, sir.
let me substitute this as a t plus b instead of x. I substitute as a t by b. Okay.
So we can use the standard integration formula on the this function.
Okay, but how do you use the standard integration formula on this function?
Like we can write it as
Huh.
at plus b to the power n plus 1 upon n plus 1
A t power a t power
a plus
b.
at
Okay, a
plus
t
b,
plus power n plus. Okay, yeah.
and then divide it by the coefficient of t.
Coefficient of t, which is basically a, right?
Yes, this is also true, no?
Uh, Basically, you are telling this formula is this is equal to this. You are claiming this is true.
Yes.
Yeah. So basically, here what you're doing is the same idea that we are doing here. So what you're
Okay,
doing
is
is
it
we are
same?
substituting. You're substituting u equal to at plus b. Now you will get a du equal to a dt. So that means, sorry, here I have to write a dt. So let me put here. So you get dt is du by
Oh, okay.
a, right?
Understood. So
So
it's basically the last step of the substitution.
yeah. So now you are substituting, instead of this, you are substituting u, and
Mhm.
instead of dt, you are substituting this term here.
Okay, so they are the same thing.
Okay, yeah, it's the same thing. In fact,
All right.
what the method of substitution is more general. It does not necessarily restrict yourself to x power n. Whatever the functions you can do, you can do. So, yeah, in some sense, it's a little bit more general.
All right, sir. Understood. Thank you so much.
Yeah, yeah. So this is a one type of substitution. So, but the other type I didn't prepare a problem, unfortunately. Just now I remember. So what we are doing here is uh, instead of a term, we are substituting. How do you say? We are putting u, right? This is one way of substituting. Another way I will tell you, it's little bit different. Uh, so suppose I have a function, but I need to get a correct function. Mm, yeah, I have to get. I thought they're different, so I just want to. No, no, it's yeah, okay, good, good. See, if you have a doubt, you feel free to ask, okay? Because we have a lot of time to try, and we can ask. If it is a long doubt, maybe we can ask towards the end of the course, end of the class. If it is a short doubt, then you can ask in some time. Okay, I just wanted to give one example, but I don't know how to give it. Okay, so what I want to probably I will not give an example, but maybe I'll just do something like that. I'll just tell you what is the substitution. Probably next class I will give an example, because I don't want to create exactly. I mean, right away I was not able to create, and I was also how to. Yeah, so a lot of things going on in mind. But anyway, so one thing what we did is, if you have something like x plus one the whole square, or let's say something like you have e power x square, something like that. If you have, then what you can do is you can substitute u equal to x square, right? And this term will now become e power u. So this is one way of substituting. Another way is suppose let's say you have a term uh, okay, let's say you have a term like 1 minus x square, okay? Under so you have integral with some domain here, and the domain has to be suitable. uh, let's say now you want to do this integral. I mean, you can directly do it, that's why I don't want to so let's say you have something like this, okay? You may able to directly do it, but let me try to give, probably just give me a minute. I will give you uh, the domain also. So I want to give this to, probably just give me a minute. Maybe I will figure out example, because it will be useful. So let me put 0 to 1. Okay, it doesn't matter, I think. Okay, suppose if you have a integral like this, one way to substitute this integral is basically, you take this term as and then you put u. So one way to do this integral is you take u as 1 minus x square, and then you do the substitution, okay? The another way to do it is you take u to be some sin z, something like that. I mean, in this example, this may be easy one, but there are examples in which one can do this kind of substitution. So but one has to be very careful that this domains etc has to match us everything, okay? So wherever sorry x is equal to sine, x is equal to sine z, okay? But you have to make sure wherever the x is defined, in this case it goes from 0 to 1, uh, there is a, so there is a domain in z, which in this case it goes from let's say 0 to pi by 2. So probably I'll write here. You have 0 to pi by 2 here, and it goes to 0 to 1. Basically, the function is a sine. Is it? You have to make sure that this goes into that domain. Then only you can make this integration possible. And it's also, I mean, there are certain conditions on it has to do it because it has to be some kind of a bijection. Okay, I'm not so sure if you need a bijection, but yeah. Yeah, I mean there might have to have some conditions, but at least the domain has to match. Okay, when you have such a thing, then you can substitute instead of x, you can substitute sine z. Okay, then what happens is you have integral 0 to 1 square root of 1 minus sine z. Okay, and now what is dz? So dx is nothing but cos z dz. Okay, and then you substitute here. Uh, So this is sine square cos z dz. And this, if you compute it, is 0 to 1. No, and you also have to change this domain here. Okay. So it has to be some kind of bijection. And let's say at least when you have bijection, it works. I don't know if the bijection is uh, necessary. Okay. And look at what happens with these things. So when the time it is 1, you will have pi by 2. So it goes from 0 to pi by 2. Okay. Why? Because you're integrating from x equal to 0 to x equal to 1, right? So that means when x is 0, your z is also 0, right? And when x is 1, your z is pi by 2. So now you have to change here. Okay. So instead of you are integrating from 0 to 1, you are integrating from 0 to pi by 2. So this, if you look here, this will be again. So this will be cos square x, square root of this. Sorry, cos square z dz. And if you integrate this 0 to pi by 2 cos square z dz. Okay. So not cos square z, cos z dz. Okay, or in some sense absolute value of cos z dz. Cos z dz. Let's just make sure 0 to pi by 2 cos is positive, right? Yeah, cos is positive, so we don't need to put absolute value. Okay. Now this function you can again integrate. It is 0 to pi by 2. You have cos square z dz. And then yeah, in this case it's not giving me anything very useful, but what I'm telling is sometimes what happens is your function may be very complicated. While doing this kind of substitution can also help. Okay, so I'm just telling there is two type of substitution. It is not necessary that in this particular problem the substitution is useful, particularly useful, and because anyway you are end up getting some term here, and I mean either you should know the derivative of antiderivative of this, otherwise you have to make another substitution. But there are exist a time where this kind of a substitution is useful, but probably I just make sure what are the hypotheses under which one can do this substitution. Okay, so the thing is sometimes hypothesis really matters, and since I don't remember, and it's been a very long time since I have studied this integration, maybe 8 or 10 years, I don't exactly remember the hypothesis, but under certain conditions you can do it. Maybe this I will do it in the next class. Okay, so just to tell you, there is two way you can substitute. Usually people do this, see it as u, but you can do this kind of substitution. This is entirely different from what it is. But anyway, this I will leave for this time. I will erase here in some sense, or maybe I'll just leave it here. but I will put a, some danger mark because I haven't done it properly. So let me write the danger mark. Yes, trigonometric substitution of integration we used to. Yeah. So, I mean, if you remember, these kind of substitutions are actually helpful while doing certain things. But just that I didn't want to create an example at the spot. It may not be very easy, and also I don't want to do much also. I mean, I don't want to do right now because I may lead up somewhere else. Okay, so maybe these two type of substitution we will do it, but at least you try to see the difference between these two substitution. Okay, they are not the same. They are both are substitution, but a different type. One is you are substituting this value, but another one is you are substituting for this value. So there is a difference. I just want to see there is a difference. If you already know the technique, also try to see the difference. Okay, so let's do another problem here. But right now we are doing this type of substitution. Okay, and probably this I will do it in the next class with a proper example. Okay, this time yeah, because I don't remember this while preparing. Just when I write the substitution, I remember, oh, there's another type of substitution. Okay, so let's do one more example of this type, substitution type. So yeah. So let's say this example. Okay, integrate x square root of x plus 3 dx. So the thing is, if you have already seen this examples, then whatever I am doing here is very obvious. But if you're new to it, then yeah, it's interesting. So let's do the substitution. So here you have x plus 3. We don't want x plus 3. So let's make a substitution. U equal to x plus 3. Then your x here. So what you do with this x? If you put this as u, but then this hangs as s, right? So we don't want x here. The reason we put a substitution here is the square root is hard. Okay, so we don't want, if you have a square root of x, then you can write this as x power minus 1 by 2. Okay, but if you have square root of something, then it's very hard to do. Okay, so we don't want a term with addition inside the square root. Okay, that's the idea. I mean, we will do something and I will tell you what exactly changed it here. So we made the substitution, but this also tells you x is nothing but u minus 3, right? And of course, you have dx is nothing but du. So let's make the substitution. This x square root of x plus 3 dx. This is nothing but now we are making all this substitution here. And this is square root of u dx. Okay. So if you ask me, okay, what do you did? I mean, you're just substituting, but you can see what interestingly happens here is whatever the addition here that I have here with the square root. See, I cannot distribute that x inside, right? Because I have a square root, this stops me from distributing here. But whatever I do here, translate this, arithmetic into here. So if you look here, I got this. So I kind of take these things, this addition, I mean, it became a subtraction, but this operation, this additional term come out of the square root. Okay, so that helps me uh, because now I can distribute. Okay, as long as I have square root, I cannot distribute, but now it makes my life easy. Now I can distribute. Okay, so when you make a substitution, sometimes you have to see. Okay, see if you have many terms here, for which term you make a substitution, the question will come, right? So you have to see which term, which substitution makes your life simpler. Here you can see this square root makes my life harder, and somehow I have to, not even the square root and plus the additional term in the square root makes my life harder. See, if this term is not there, it is not very hard, right? It is x power 1 plus 1 by 2, which is basically 3 by 2, and you just apply the formula x power n. But what makes it harder is this term, and you don't want that term to be here, and that's why we make the substitution here. Okay, from here onwards, I think it's not very hard to proceed. we have done these problems, right? So this is integral u power 3 by 2 minus 3 times u power 1 by 2 dx. Okay. So I will probably just write the solution here. Maybe you can try to figure it out what it is. Okay, it's 2 by 5 u power 5 by 2 minus u power 3 by 2 plus c. Okay, so this is what we have. But remember, u is x plus 3. So come back and substitute it back. Now, whatever this u is, it is x plus 3. This is 2 by 3. So this is x plus 3 power 5 by 2 minus x plus 3 power 3 by 2 plus c. Okay. Okay. So much. So far, it is good. I just want to ask you one question and then we will proceed. I mean, it's not a very serious question, but just wanted to tell you. So let's say I have this function, okay, f of x. So let me write something like that. If your capital F prime is let's say f, and if your capital G prime is let's say g, and you take the you have the integral of f plus g you're taking, let's say dx, and this is nothing but integral of f dx plus integral of g dx. So when we write it, what we get is f plus let's say some c1 plus g plus some c2, right? But we are not writing like that. What you are writing is we are writing it as equal to f plus g plus c, right? So why you can write like that? I mean, there is nothing big going on here, but I'm just asking. So yeah, exactly. Because C1 is a constant, C2 is a constant, but then, I mean, you take this two constants, C1 plus C2, it's again a constant, right? C1 can be any number, any real number, C2 is any real number. If you add it to real number, you will get a real number. So whatever this number is a real number, right? So why do you want to write two of them when you can just add it and then just call it as a C? Okay, so that's what you're doing. So whenever we write it, since we split it, we do it, and we are not doing like that. I just want to tell you that it's the same. Okay. Okay. So basically, I'll write here. Maybe if somebody just reads the notes, add C1 and C2 and call it C. Anyway, so probably we move on to different section, which is basically integration by parts. Okay. So now, one of the interesting thing with, if you remember with the differentiation, is you have this formula, right? D by dx of uv. If you take it, it will be nothing but u dv by dx plus v du by dx, right? This formula you remember. So this is called the Leibniz rule. I mean, because it was given by Leibniz. Okay, so this is an interesting formula, but what we are going to do is we just modify it a little bit. Okay, so we take this term to the other side. So you have integral d by dx uv minus u dv by dx is nothing but v du by dx, right? So we have this. Now what we do is we integrate on both sides. Okay. So when you integrate, what happens to this term? So this is basically antiderivative of derivative of uv. So can you tell me an antiderivative of derivative of uv? It's basically uv, right? uv is one of the antiderivative. Okay, so you have uv minus integral, uh, just give me a minute. Yeah, okay, okay, probably I will do, see, this is, there is some symmetry here. uh, so in some sense it doesn't matter whichever the one you take, but I will take the one which is, very standard use, because we all remember that. So I will just do it here. So I can either move this thing to here, or I can move this thing to here, and it doesn't really matter. One of the thing we move. So we keep this, let's say, and we move this to the other side. Okay, I did it here little differently, but we will keep the version that which we usually, kind of remember. I mean, I'm telling you because in most of the books, the same thing, but it up to a symbol is, there's no difference here. It just the name is different. Otherwise, there is no difference. Okay. So one of the thing we can take, without loss of generality, let's say we take this here. I mean, because there is a inherent symmetry, just two function, product of two function. So this is v du by dx. Okay. So this is nothing but integral u and dv. Okay. Or if you want to write it as without writing this dx, then you can write so this is dv by dx. So if you want to write, sometimes people like to call integral u dv is nothing but uv minus integral v du. Okay. So basically what we are doing is, in some sense, we are kind of reversing the Leibniz rule. Okay. Yeah, in some sense we are reversing it. Basically, you take the Leibniz rule, and then you apply the integral on the both sides. Okay, so that's what we are doing, and we got this familiar formula, especially if you have done your math in uh, schools. Okay, so this is called the integration by parts. Okay. The thing is, this was always confusing for me when I was doing, in the school. So I always wonder whether you have to write UDV or VDU or something. I always write, but it doesn't really matter. Okay. Anyway, so you have to do UDV is UV minus integral VDU. Okay. So you remember the formula. So now let's move on to different problem. So another thing is, if you probably in the school, and especially in the tuition, they will tell you what are the things one can take as u, what are the things one can take as v, right? Do you guys remember that some mnemonic or something they will tell, right? If one of you remember, you can tell me. So there
We
is,
have listed it as islate.
okay, I will just maybe write here if somebody is interested. uh, okay, so what is the I stands for? Is inverse, right?
Yes, sir.
And this is a logarithmic. What is this one?
Algebraic,
Okay, algebraic.
trigonometric, and exponential.
Okay. So this is a choice. It goes in this direction or the other direction. I mean, which one we should take first? It's inverse is what we take first, right? And okay, can you explain for V or U which choice you take it?
These are the choices for V, and
Okay.
it's given priority from left to right.
Okay. Thank you.
I hope I remember it correctly.
Yeah. Choices for V and a priority from okay, left to right. Okay. I mean, I don't remember it, but we just you can verify it. It's not So just verify with your school teacher or something. I don't know. I don't know with whom you verify, but yeah, you can verify. So the thing is, well, I have one way to explain it. What we choose is depend on the situation. Okay, you look at the problem. This is fine if you not able to see it, but somehow you should have an intuition without any of this, that if I look at the problem, which one is creating me a problem and how can I eliminate it. Okay, that is the real thing what we are going to do. For example, here when you look here, so what we have seen is the problem that stops us doing it is this square root here, right? And we want to eliminate the square root, and hence we did the substitution, transfer this algebraic thing to the other side. Okay, so that's what we did here. And similarly, we are going to take one of that as u and one of that as dv. It depends on the situation, and if you can't able to figure out, then probably this expression might help. Okay, so order of creating in this direction. So my math teacher also told me, but I don't remember it, and I never used it. So I was like, well, see, because the problem with this is it's not necessarily universal. There can be a formula in which this may not work, but most of the times this is the intuition and one can use it. There's no issue with that. Okay, but usually I prefer not to use it, but it will be useful at times, because whenever you want to compute quickly, uh, you don't have to think much, and then you go in the order of precedence. It will be very helpful, especially when you're doing some examination or something. But when you do without the examination, you try to see what exactly helping you, because that will help you to develop a little bit of better intuition than following a formula. Yeah, you are telling something, right? You can ask me.
Yes, sir. Can you please just correct the um, thing? It's choices for you. I just verified it.
Ah, okay. Thank you. Thank you. So the thing is, I know they say this, but I don't remember which direction, etc. So you guys might be uh, very familiar with that, so I just wrote it here. Okay. Because I mean, I didn't took a tuition, so my teacher did it in the class, and one time she did it, and I didn't even want to listen at the time. But but later I realized, see, at some point I thought, okay, okay, you're doing something, so what the point? I can just look here and I try to find what is what. But especially when you are under the pressure in the examination or something, having these kind of things might change whether you can solve it or not. So but when you are free and do it, try to do by yourself without having any this kind of thing, so that you have ability to develop intuition. Okay, what is basically what you're telling is what is the abstraction, and how I am going to see, we know there are certain formats, and this integration part is a method, and if you realize, okay, this is the method I'm going to do, now it's a matter of trying to see which one to put, which makes your life easier. Maybe you may need a few trial and error, but you can do it. Okay, so let's start with the problem here, and maybe we go quickly. So let's start this problem. Integral x e power x dx. Okay. So so here what you can do. I mean, one of that we are going to take it as dv. So if you come here, one of this we are going to take it as dv. Another thing we are going to take it as du. But you remember, whatever the dv comes here, that becomes a v here, right? And whatever this u comes, now we are going to put below. And if you look, this is just u is just x here. Okay. In this case, what you can see is uh, this exponential function here, right? If the exponential function is, if I see my exponential function as a dv, and if the exponential function come here in the beginning, okay, then what happens? Because it's easier to integrate the exponential function, right? So since it is easy to integrate exponential function, it is in my uh, I mean, it's good for me if I kind of take this exponential function as, take this as dv. You want to take this inside and call it as dv. Okay. So if you want, you can write it as integral x, d of e power x. Okay. You can call it as, and in some sense, if you want to write, this is u, and this is dv. Okay. So this is dv. Okay. So basically, this is what we are going to write. And if you write here, and this is nothing but integral, mm, sorry, this is uv. So this is x, e power x minus integral uh, v du, which is e power x. So u is basically, okay, I will write here. Our u is x, our v is e power x. Sorry, e power x, not e power x. So this is again, it will become just a dx. Okay, and this integral is easy to do. It's nothing but just e power x. Okay, and then put a c here. Okay. So it depends on the choice. Okay, which one you want to do first. That what matters, and you choose something which makes your life easier. And the idea here is, if you want to see, the idea here is, you want to have a function which can be easily integrable. That is the idea here. And if you have, let's say, exponential function, let's say in the front, if you have exponential function, that will be easily integrable, and hence you want to choose the exponential function. Okay. So if you look here, let's say you have given me a mnemonic here that the order of priority goes in this way for choosing the u, right? So, for example, exponential is of the least priority to choose the u, because exponential function works very better when you have a, choose as a dv, because it comes in the front and it's very easy to integrate the exponential function here. Okay. Uh, so that was the idea. So, and hence you can put it as a v rather than choosing it as a u, because whenever you take a derivative, that might sometimes makes life easy. So it all depends. Sometimes this might work, sometimes it may not work. uh, I don't know, but you have to make a proper choice here, proper choice of u and v. That really matter. So probably here you keep it as exercise. Okay. And I will tell you, choose uh, u to be differently. Okay. So let's say choose u to be e power x, and choose v to be 1 by 2 x square. Let's say, I think this will work, right? So I have to see this as dv. Okay, so x dx should be equal to dv. So if I take this, take the derivative, yeah, that will work. So choose this and see what happens. Okay, and try apply integration by parts. Okay. Uh, thing is, it will become very hard to do it. Okay, it will make things very complicated. Sometimes you have to choose the things properly. Okay, here you try it, but you may not get much out here, because it will just makes your life complicated. Okay, here's a hint: if you don't want to try it, uh, it will be complicated. More complicated. So the proper choice of u and v actually matters here. Okay, so some choice will help your life, some choice will make it horrible, but yeah, so you can try it. Okay. Honestly, but does that series converges to Sathasivam? Uh, I don't know. I mean, you have to try it. I mean, if it converges to solution, then you have to tell how it is converges. So it may not. I didn't check it. Uh, but what I see is if you do the integration, you will end up with something like 1 by right here. Probably use the proper one, and maybe I'll change this color also. This is a stupid color. Okay, this is better, I think. Still not good, but it's better. Okay, so you will end up getting something like 1 by 2 x square e power x minus integral 1 by 2 x square e power x dx. Something like that you will get, and then you have to use the integral by parts again, and then you will keep going. I think that is what you mean by infinite series, if I'm right. But whether that does that converges, yeah. So basically you apply integration by parts again here, and you will get already one term. Now you will get another term, and then probably something in the x cube or something will come, probably 2 times 3, I guess, if I'm right. So there will be more and more time you will keep adding, and you may not achieve much. Okay. uh, so the thing is, it depends on what choice you do. Make a proper choice. So another way to say it is, you don't need I mean, okay, I don't know why I'm just going to attack that, but anyway, what I'm telling is, but good thing is you only have two choices, right? So either you can be this, or you can be this. But if there are multiple terms, then you have to choose. Okay, maybe two terms can be you, two terms can be we. But yeah, make a choice. It's up to you. But you have to, at the end of the day, you have to make a choice. Okay, so let's move on to different questions here. Maybe I can just 1 minute. Thing is, maybe this idea is good, but yeah. So I have another example here, but I leave it as exercise because we have only half an hour, and I have to do the numerical integration also. So let's say it is exercise. You compute integral x ln of x dx. Okay. So in this case, you have to make a different choice. See here, I made a choice of v to be e power x, right? In this case, you don't want to take v to be e power x, because you try to take v to be e power x, that might create a problem. Okay. So one way to do is, you write it and see what actually it creates a problem. Okay. Whenever you wrote it, you might be very easy to find. Okay, it creates a problem because you just want a term here. So you have this vdu, right? You want a term here which you can easily integrate. uh, that is the point. Okay, you just have to choose such that this term is kind of easily integrate. Do whatever you want to do it such that it will be easily integrate. So that was the thing, but it may not be all that easy. It's easy to say it, but may not always that easy to find. But yeah, but more or less you can find it. So let me skip most of the things, and let me go into something that is interesting, and then we will proceed to let's say the numerical integration. Okay, so let me start with something called the integration of rational functions. So of course one can do integration of trigonometry functions, but to do the trigonometry function you need to know the trigonometry identity. And some combination of trigonometry identities will help, but there is not much idea there. Most of the idea here we did with algebraic and exponential functions or logarithm functions. You can have a trigonometry function also. Thing is, some trigonometry come into play. Okay, only that much is a difference. But this rational function, there is a little bit different idea is that, different technique is that. So I will probably introduce that now. Okay, it's the integration of rational functions. So let me say what is a rational function. Okay, rational function. Let me call it as r of x, or maybe I'll just write f of x or r of x. So if you have function f of x which is of the form P of x by Q of x. Okay, and what is this P and the Q? Where this P and the Q are polynomials. So P and the Q are polynomials. So it's a polynomial functions such that your Q of x has to be not equal to 0 for all x. Okay, so when I say not equal to 0, it means not equal to 0 for all x belong to R. So does it for all x belongs to R? Yeah, it should be for all x belongs to R, because uh, otherwise it doesn't make sense to define these functions. Okay, just give me 1 minute and I just want to verify one thing. I mean, one thing is this is not written like that. Just it's saying for all x. But it may not give all the time. Yeah. Hey, just give me 1 minute. I just want to see one thing and then we'll proceed. So, okay, yeah. I mean, just the Q of x is not identically 0, not necessarily all this point, but those points, the functions are whatever the x at which Q of x is 0, the function will not be defined. Okay, that much is the problem there. But we just look at the places where it is defined. Okay, we don't care about the places where it is not defined. Just look at the places where it is defined. Uh, those functions are called, let's say, rational functions. Okay, so now if you want to integrate, let's say, a rational function, how do you integrate? See, this is the same thing. For example, if you have some function like x power, integrate 1 by x minus 1. I mean, one should always ask, okay, you want to integrate, but see, this function is not defined to 1, right? X equal to 1, then how do you integrate? So basically, you're looking at the function, I mean, leave that in the domain. So your function, uh, this function is defined everywhere except x is not equal to 1, right? So you consider this as a function from R difference, 1 to R. Okay, just change the domain such that this function is defined. Okay, so anyway, the similar thing you will do for here also. Since it's a polynomial function, if you have a degree n, then you only have to worry about a few terms here, right? So if you have degree n, then you have only n roots, and you only have to worry about the roots of q, but you just remove those roots from your real number, and from that domain you consider the function, etc. Okay, this f of x is not necessarily a function defined on the entire R. Okay. Okay, anyway, so now the question is, okay, how do you integrate the function f of p of x by q of x? So this is the question, how do you integrate? So first what you do is, here I think we will only proceed with only the degree 1 and 2, we will give some rule, and after that, I don't know, it will become harder, so we will not proceed to that. But I mean, but the same technique, almost the same technique may sometimes work, but you have to see. I think it will work only, but I have examples whose degrees are 1 and 2. Okay, so let's look at the case where the degree of q of x is equal to 1. Okay, and let's say we consider a problem directly. We go to the problem and see it. So let's say I have a problem like this: x square plus 3x plus 5 divided by x plus 1 dx. Okay, now how do you integrate this problem? Okay, what we are going to do is we are going to use the long division, or we are going to use the division algorithm. What you are going to do is we are going to divide this polynomial by this polynomial, write it as a quotient times a remainder. Okay, so that is what we are going to do right now. So let me write it as some quotient times remainder. So let's consider your function. I'll write here. We'll do the long division, x square plus 3x plus 5. So we do the long division with the x plus 1. So I have to multiply by x, and that gives me x square plus 2x, right? And I'm subtracting it here. So probably x. And so that leaves me uh, x plus 5. I need to do it, right? So that is the thing. So basically what I'm doing is if I multiply this term with this term, what I get? I will get x square plus 2x, right? And I'm just subtracting that with this polynomial. That will gives me whatever the remainder I want. Okay. So multiply with this with this.
So it will be x square plus x, I guess.
X square plus.
X x square plus x.
Okay, okay. Sorry.
It's all right, sir.
Yeah. So we have this. Okay. Now, okay. Now there is a
So
division. Uh,
plus. Okay, the plus will get minus. Okay, sorry,
yeah,
sorry.
I'm just subtracting that, and this is the remainder
Hmm.
here. Now this term also we can do the. I mean, we can again divide this term by that term. So let's divide this. This will be 2x minus 2. So basically, I'm just I mean, I'm just doing this term, and then I'm basically subtracting here. Okay, so I'm doing 2 times this, and then I'm subtracting with the remainder. Uh, when I do that, what will I get? I'll just get the 3 term 3. Okay, so I can write now. I can write x square plus 3x plus 5. This can be written as x plus 2 into x plus 1 plus 3, right? I can write like that. See, if you want to see basically what I'm doing, why I'm subtracting here, I think if you remember the long division, it's fine. But you want to see why I'm subtracting, what I'm doing is first I take this and then I take this term. Okay. So I'm computing x into x plus 1. Okay. And then I'm subtracting it to here. Okay. When I subtract it to here, I get 2x, plus 5 I get. Now in this 2x plus 5, I'm just subtracting x minus 1 again, or maybe 2 times x minus 1, and then whatever the remainder I get. That's what I'm trying. Basically, I want to find some term here such that when I multiply and subtract, uh, I will get some product of this times the remainder, right? So what I'm
Yes,
doing is
sir.
every time what I'm doing is this term in the front is a polynomial, right? So it should be a polynomial of, in this case, it has a x square term. So this polynomial has to have, some ax plus b, right? It should be of this form. So what I'm basically doing is I'm just multiplying this ax of this ax into x plus 1, and then I'm just subtracting it so that the first term will go away. Okay, I'm just like figure out, okay, a is 2, sorry, a is just 1, we subtract and leave out. Okay, this you try to see why it is true, or if you do you have a doubt of why I'm doing this. If you have a doubt, you let me know, I can try to explain it properly.
No, I was just a bit confused. It's all right. I understood it now.
So basically, what we are okay. Let me take a minute and then probably say it properly. So what we are trying to do is we are trying to multiply certain terms with this and try to remove each of the things. Okay, so and if you want to do it here, you probably see it like this. You see I'm writing ax plus b times x plus 1 plus 3, and then you multiply it, and then take it to the other side. Somehow if you find the a, in this case a is 1, so maybe I'll write it properly. So this is ax, or maybe ax, capital Ax, into x plus 1 plus b into x plus 1 plus 3. Again, this is x square plus 3x plus 5. Now you just subtract it here. Okay, so you want x square here. That means my a has to be 1, right? So okay, now my a is 1, and then you subtract it, and whenever you subtract it, it will become equation in b, and then you can find the b. Okay, so that's what we are trying to do here. Okay, okay, and this will also some c. This is not equal to 3. This is some c. Let's see. Okay, so now so basically you have to solve this equation. You solve it, and then you will get it. Just collect the terms and solve it, you will get it. That basically the same thing I'm just doing here systematically. Okay, maybe I will collect one term and then leave the rest. If you just collect, take everything to here and collect just the x square term, what do you get here? Ax square plus x square plus some terms in x, uh, plus a constant term, right? So from here you can observe that a plus 1 x square plus some terms. Sorry, a, not a plus 1, a minus 1. Okay. So that implies a equal to 1. And similarly, we do b. I mean, from here, from the next one, you compute the b, etc. So that's the same thing. I'm just doing it here. Uh, okay, anyway. I think I made it much worse, I think. But anyway, what you can do is you can do the long division, and you can write your polynomial as a product plus quotient plus a remainder, right? So what we essentially got here is this term x cube plus 3x plus 5. We want to divide by x plus 1, and then you have to integrate it. But what we observe is this the top term is nothing but x square, sorry, not x square, x plus 2 times x plus 1. Okay. Yeah, so it will be x plus 2 times x plus 1 plus 3 divided by x plus 1 dx. Okay, so this is what we got. Now you just cancel out these two terms. So this will be integral x plus 2 plus 3 by x plus 1 dx. Now we know how to take the integral, right? This is nothing but this is what? So this is x square by 2 plus 2x plus, this time you do the substitution here. Okay, x plus 1, take x plus 1 as u, and dx will become again du. Okay, du is equal to dx. Okay, so do the substitution, and then you will get this nothing but 3 times log, basically natural logarithm, x plus 1 plus c. Okay, so if when you have a term like that, what you are going to do is you sir, it's not x cube, right? It's x square. Made error. Okay, so our problem is x square, not x cube. Okay, so when you just do the long division, and you can do this thing. Okay, this works. So, but on the other hand, not all the problems are like this. What happens if you're whatever you're dividing all has a degree 2? So this works for any problem, whether you have a x square, x cube, or x power 4. Anything works as long as the the bottom degree is 1. You can do this. Okay, What if the bottom degree, the polynomial in the denominator, if the degree is not 1, let's say 2. Okay, so let's do the next part. Degree of q of x, let's say it is 2. Okay, in this case, how your q of x looks like? Your q of x looks like ax square plus, let's say, bx plus c. It looks like this, right? Now what happens is your p of x by q of x, if you look this one, this will looks like, I mean, you do the long division first. Here you start and do the long division. Okay, you will get the polynomial a of x, some polynomial, plus there is a remainder here comes, which will be rx plus yes, plus you have this x square plus bx plus c. This is clear, right? We do the long division here and then we divide it by q of x directly. Okay, when you do long division, what you get is p of x is equal to some a of x, some quotient times q of x plus some remainder of x, where the remainder has a degree strictly less than the degree of q of x, right? Since I have a degree of q of x is equal to 2, that means the remainder has a degree 1, and any polynomial of degree 1 is a linear polynomial of this type. And I'm dividing everywhere by q of x, and you end up getting here. Okay, now what happens is you end up with see, this you can integrate. It's a polynomial you can integrate. I mean, I leave up to you. So this is the term of our concern. How do you integrate this? Okay, so let's take a solid example and see how do you integrate. Okay, so let's look at the first example. But here what happens is it depends on the discriminant of this polynomial. You have to do differently. So you have look at the discriminant, which is a b square minus 4ac. If it is depend whether it's strictly greater than 0 or a discriminant is equal to 0 or discriminant is less than 0, you might have to use a different rule. But I will tell you what's the general idea, and then you can try to find. Okay, so let's say we do one problem here. So this is integral, okay, 5x minus 7 by x square minus 2x minus 3. See, the thing is, now I think we have only 13 minutes. I want to do the numerical integration also. I'm not sure if I can do it. So let me try to catch it up quickly here. So this will be, I mean, you take this term and you write it as, so take the term 5x minus 7 by x square minus 2x minus 3 and write it as a by x minus 3 plus b by x plus 1. Okay, now you have to find what is a and b. So how do you find it? You just cross multiply these terms and compare. That's what you're going to do. Okay, so when you cross multiply, what you get x plus 1 times a plus x minus 3 times b, which is equal to see, it is the same thing. Okay, so see this term. Okay, how do I write like that? Why these two comes is basically because this denominator, if you look, since, okay, the first case I am dealing is you look here, you have your delta is greater than 0. If you look at b square minus 4ac of this polynomial, that will be strictly greater than 0, and it has two real roots. And the two real roots are basically x minus 3 and x plus 1. So this polynomial can be written as x minus 3 into x plus 1. Okay, so that I'm writing like this. Okay, so I'm writing this as two such things, and this is basically x minus 3 into x plus 1. Now what happens is you look at the denominator are the same, so I can cancel the denominator and I can just look at the numerator. Okay, how do you cancel denominator? Take this polynomial to the other side and basically cross multiply and then cancel out. Okay, So this tells you 5x minus 7 is nothing but x plus 1 times a plus x minus 3 times b. So from here you compute that if you do it, you will get a equation of the type a plus b is 5, a minus 3b equal to minus 7. Okay, so from here you can compute a equal to 2, b equal to 3. Okay, so how do you compute? You just multiply here and then compare with this. Okay, so probably you look at what happens with the x here. So the x comes from ax here, and you have a bx here, right? So here if you just compare x, you will get 5x is equal to ax plus bx. That gives you the equation a plus b is 5. Okay. So and then you have two system of equation. This you can easily compute what it is. Use the elimination method or some other method. You can compute this equation. Okay. Now your integral became integral 5x minus 7 divided by x square minus 2x minus 3 dx. Your integral became 2 by uh, x minus 3 plus 3 by x plus 1. So you take the integral dx. Okay, so now it became like this. Now this integral is easy to integrate, right? This is nothing but ln of x minus 3 plus, I mean, you have to do a substitution here, but we have done it multiple times, so I just left it x plus 1 plus c. Okay, so here we were able to do it. Of course, probably one can do other problems, but let me go to the case 2 here, where let's say your delta is equal to 0. Whenever the delta is equal to 0, what you have is you have multiple roots, right? So your polynomial, which is ax square plus bx plus c, if you write, this will become a times x minus x1 the whole square, right? Your polynomial looks like that. Now what you're going to do is you want to compute basically you have something like a by b, or maybe not a by b, rx plus s. You have term rx plus s divided by a x square plus bx plus c. See, this is the term that we are trying to integrate here. If you look here, where is it? I mean, I do the this we have done it, and yeah, you remember here. This is the term that we are interested. Because this polynomial after long division you can integrate. This is the hard thing to integrate. So whatever we are doing here, the examples are of this form. Okay, so the same form I'm writing it here. This. So one thing what you can do is this polynomial can always be factored as a partial sum of this form. Okay, so where this x1 is the root here. Okay, or if you don't want to write x1, I can write alpha, but I think it's fine. So you can always write it of x minus x1 square. Okay. Uh, well, why do you need a why are you putting a square here? Okay, so that is something to think. What if I just you know instead of square, suppose if I don't put it, then what happens? So you think about it. Okay. Uh, so any idea why you need a square? Because I have to see basically here. How do you add these two things? So when I have two different roots here, then when you add it, what you have to do is you have to take the add it to the LCM, right? If I don't put a square here, then what happens is if you take the LCM, what will you get? So you think about it. If you take the LCM is just the same thing. So if you don't put a square here, then what happens is you will get just a plus b by x minus x1, and that's not going to end up with whatever you want. So you want the square here because your polynomial is x minus like this, right? Your polynomial has a square, so you want a square term here. Okay, now the question is, okay, I have a square term here, no worry. Uh, then why not I put a square here also? If you put a square here also, then if you look at just the addition is nothing but a plus b by x minus x1 the whole square. But a and b are constant, so a plus b will only give you constant. But we need a rx plus s. Okay, so since you need rx plus s, you cannot take a square here also, or you cannot leave the square here also. So this is kind of the perfect uh, structure such that when you want to take the LCM is a square, so you need to add a x minus x1 here, uh, and then you take the square and you do it. Okay, so without going to the detail, what you do is you express uh, your function in terms like this. Now you can integrate both sides. Okay, and it's a very easy integral, and it's the same thing. Now you can just integrate it, and that will solve the problem. Okay, so how do you integrate when there's a square? You basically do a substitution, and then you will integrate with the formula. See it as x power. You do a substitution. Let's say u equal to x minus x1, and then that became u power minus 2. So it will become b u power minus 2 plus a. This became ln, of course, and then you can integrate. Okay, so the integration is not a problem. And how do you find a and b? A and b you can find exactly like how we find here. Okay, so I'll just leave it as exercise. But when the delta is less than 3, when you have this discriminant here, if your discriminant is less than 0, then what happens? Then you will not get any real roots, right? So when you don't have a real roots, uh, it does not seem okay. When you don't have a real roots, you cannot do this term. You cannot do the partial fraction, right? Because the partial fraction uh, depends on the fact that you have a real root, and your denominator can be written break down into product of these two things, these two roots. If you don't have a real roots, then you cannot use the partial fraction. But I think this type of problems also one can do, but it involves some trigonometry function and all, uh, which we are not going to do. We just say partial fraction does not apply. Okay. As there is no real root. Okay. Yeah, by the way, is the any of you here is the so maybe Advait, I can ask you, is the Simpson rule and trapezoidal rule is done in the class? Oh, it's no. Okay. Then probably okay, so we might have to do that also. Hey, is that done in the other tutorial? I don't know if you attended that. If it is not done in the other tutorial, then probably I will try at least to give the idea. Maybe I have to do something. Oh, it wasn't done. Okay. I see. Yeah, then I should have skipped some of this integration techniques and I should have went into that directly. But unfortunately, we end up in a situation where we should not end up. Okay, so just give me a minute. So let me write a problem directly. This is not usually the way I do it, but let me write a problem directly, and then we will today we will do it like a formula, just a formula and a problem without much details. Uh, so that at least you know what is the formula. Of course, you can look at the internet and figure out the formula. Uh, but I will just write the formula and we do it. Next class, we will start with the Simpson rule and the trapezoidal rule. Probably I will give you some idea and maybe proof of whatever it is. Okay. So let me write a function here. Let's say f equal to sine x. Okay. And we use the both the let's say the Simpson rule and the trapezoidal rule. Okay. So probably I will just go over 5 minutes. Maybe I will not go over that. Maybe 5 or possibly 7 minutes. I'm really sorry about that. Uh, Simpson rule. But on the other hand, the video will be uploaded, so you can watch later. If you have some work, you can go and you can watch later, of course. And the next one is trapezoidal rule. Okay, so I will come back to the theory in the next class. So basically, what Simpson rule does is you have a function here, and you want to approximate the function. What you do is you fit the best possible parabola, and then you approximate it. Okay, trapezoidal rule is much simpler. Let's say I have a function like this. So here you have a sine x. So maybe it will be covered in week 6. But you have a assignment in week 5 which has this problem. That's why I worry about it, right? Otherwise, I will not be worrying. I have seen at least 1 or 2 assignment problem. So just in case if you want to know at least the formula, so I should give. That's the thing. So basically, what the Simpson rule does is it approximates your area using a parabola. And trapezoidal rule is much simpler to state. What you do is you, let's say you choose 4 points here. Okay, and maybe I will tell you sin x. Compute uh, integral f of x dx with the points with the 4 points basically with 4 points of equal, let's say equal length. Okay, so you want to find the area of the sin x, right? That is basically integral. Instead of that, what you are going to do is you find the 4 points here. Let's say you cut it into 4 equal points. Okay, and then you draw a trapezium in there. Okay, so now instead of finding the area of your original sin x, what you do is you find the area of the trapezium. Okay, and the area of the trapezium kind of gives you the good enough approximation uh, to your original area. Okay, and that is basically the trapezoidal rule. The Simpson rule is basically you approximate the curve with the parabola. Okay, so these are the two things. Now what we are doing is see, what we are actually doing is, so far what we did is we actually try to find a rule that directly gives you how to find the integral, right? What happens is sometimes you cannot directly find the integral. The function can be so complicated that you cannot actually find the integral. So here also we have some problem like that, right? So whenever we take the uh, things differently, so for example in this case when you took it, choose the different you have seen the it became hard problem, right? So but that is if you change the integration by parts you will solve it. But things there are problems which you cannot integrate, because to integrate means you have to find antiderivative, right? In general, finding antiderivative is not easy. So what we are doing is, okay, let's not find antiderivative, but let's use the first fundamental theorem of calculus. Integral is nothing but the area, right? So if you want to find the integral, at least if you want to find the definite integral, let's say from a to b, so this you can see it as a area under this curve using the first and second isomorphism theorem, right? So now what I do is, okay, if I cannot find the area directly, you just approximate it. Okay, and that's where the numerical integration came into picture. And there are two methods to do it. There may be many methods to do it. Two of the very popular methods are Simpson It's also called the Simpson 1 by 3 rule. There is other, I think this number will be changing and there are different rules are there. I don't remember the number here, but at least Simpson has more than 1 or 2 or 3 rules. Okay, it's not exact. This rule is called 1 by 3 rule. Okay, so I will give the formula here. So let's say I have this 4 points. Let's say I start with this x0 and x1. Let's say x0 and this is not x1, but let's say in this case x4. So this is x1. Okay, just give me a minute. X2, x3, x4, right? Yeah. So basically, I'm cutting this 0 to pi by 2 into 4 pieces. Okay. Sir, 0 to pi by 2 or 0 to pi? Yeah, 0 to pi. Did I write 0 to pi? Okay, I need to write. This is an indefinite integral. Probably it will be coming in the next class because it's an indefinite integral, as you said. I didn't also look at the week 6 because it's a definite integral, not an indefinite integral. Okay, so let's say this is 0, pi by 4, pi by 2, 3 pi by 4 and pi. Okay, so basically you are cutting it into 4 pieces and basically finding the area of this. Okay, so let me call this point I mean this y points as y0, y1, y2, y3 and y4. Let's say, I mean, of course y0 is this points, not exactly that. Okay, so if you call like that, where y is basically the f of x1. Okay, f of xi is yi. So by this I don't want this. See, this is y1. Okay, this is y2. Okay, suppose if you have these 4 points, then your trapezoidal rule, not trapezoidal rule, Simpson rule states the following. This is Simpson rule. The integral, the definite integral is nothing but delta x by 3. Well, delta x is basically how many pieces you cut it, the length of that pieces. Okay, so the length of the pieces is delta x. In this case, the length is pi by 4. Okay, so y0 plus 4y1 plus 2y2 plus 4y3 plus y4. Okay, so the formula is like this, but let me not do like this. I will just write the formula a little bit differently. That would makes the life more easier here. So it's delta x by 3, and what you do is you start with y0, you put plus 4y1. Okay, and you put y2. Okay, see, this is the diagram is for trapezoidal rule, but now I'm writing a Simpson rule formula. So yeah, please keep that in mind also. And then plus you start with y2, 4y3, and then y4. Okay, so this is the formula. So what you do is you take 3 points at a time. Okay, so first point, second point, third point, 3 points at a time you take. The first one you keep it as like this. The second one you put a 4 and then keep it as like this. Third one you just stay. Okay, now you start from this point. Third point you take 3, 4, 5. Okay, you go 3 points at a time. Okay, if you want to do Simpson rule, you have to have a you have to take 3 points at a time. Okay, so in this case 3 points at a time, 3 points at a time. Okay, so like this you will have. So this is the Simpson rule. If you have another 3 points, okay, then you can also do the same. So let's say this is x4, x5, x6, and the Simpson rule became y4 plus 4y5 plus y6. Okay, so you can add these points. So this is the Simpson rule. And if you look at the trapezoidal rule, did I wrote the trapezoidal rule? I have to check. Just 1 minute. I think this is basically 1 by 2. Okay, just give me a minute. Okay, forget that episode. Yeah, so this is basically delta x by 2. Uh, yeah, so if you cut it into let's say n sum, so n of this, so trapezoidal rule says the following. So the integral f of x dx is nothing, is approximately equal to, of course, you have to take the sum from k equal to 1 to n, f of x k minus 1 plus f of x by 2 times delta x. Okay, so delta xk, of course, but we are cutting it in equal parts, so we can just write delta x. Okay, so I will tell you what is happening here. So if you look at the area of the, I mean, this might look hard, but you just look at the area of the trapezium. So let's say I have a trapezium like this. Okay, so if you look at what is the area of trapezium, the area of trapezium is nothing but 1 by 2. Uh, okay, I have to draw a certain things here. Let's say this is A, this is B, and let's say this length is H. Okay, and these two lines are parallel lines, of course. See, this line and this line is parallel line, and this is also, in my case, it is perpendicular, but this can be anything. Okay, and the height of this is basically H. Okay, if you have a trapezium like this, then this is 1 by 2 a plus b a plus b by 2 times H. Okay, so if somebody is, thank you for explaining. Okay, so this is the area of the trapezium. Okay, basically what we are doing is H is the height. So in this case, you come back and see your height is nothing but a delta x, right? Height is a delta x. My function points are basically this point and this point. Okay, so let me call this is f of x naught x1. So what we are doing is we just sum these two. Okay, and then your so basically this is the height, right? What is the height of this? The height of this is basically where the y1 is there. That is the height of that, right? So basically we are just computing the area of each of the trapezium. Okay, find the area of each of the trapezium. Each of the trapezium has this formula. Okay, where h is the height of this. In this case, I'm just calling it as a delta x, and these two things you take divided by 2 and then compute. Okay, so this is the trapezium formula. So basically, all you need to know is, if you don't worry about this summation, etc., you have multiple trapezium. Each of the trapezium, you know how to compute. Just sum it. That's all. The area is basically, it's the sum of these pieces, and the pieces you can just sum it. Okay. And this is the Simpson rule. Simpson rule, what you need is you need three points. Okay, first 3 points you take, and the next 3 points you take, and then basically what you're going to do is you're going to find the area of the 3 points each. Okay, so find the area of this, find the area of this, and then you will add it. Finding the first area is basically gives you this 3 points. Okay, this formula, and the next 3 points can be captured by these three things. And if you have another 3 points here, then that can you have to write the same thing. Okay, you have to write y4 plus 4y5 plus y6. Okay, next class I will explain how exactly this is 4 and this is 1 and 1, and how this term comes. Probably I will explain in the next class. It is called Simpson one third rule because in the quotient there is by 3. Okay, so 1 by 3 is there. That's why it's called 1/3 rule. There are other Simpson rules also there. Yeah, unfortunately I should have managed the time properly. Since we did those problems, yeah, it became late. But anyway, you can keep the formula at least for now, and maybe try for sin x. You can easily find it. You can also, if you have some doubts, you can always ask my send me a mail. So I will just write the email ID in case. Okay. So at least these are the formulas. You can keep it. We will come back and prove that this is the Simpson rule formula and this is the trapezoidal rule formula. At least trapezoidal rule, I don't think there is much problem here, because you are just finding the area of the trapezium, and the area of each of the trapezium is basically given by, you just add the two sides, take by 2, and add the h here. So if you look here, h is basically the delta x, because we are dividing it into equal pieces. Okay, you don't need equal pieces, you can have unequal pieces. That's why the original formula has delta k here, but forget it. We divide it into equal pieces, and then you have these pieces area. You find each of them. So the kth piece area is this, and you are just summing over how many pieces you have. Okay, so that is this n is the number of pieces. Okay. Uh, anyway, don't even write it. Okay, it's just number of trapezium that you're going to draw here. Okay, trapezium rule is not very hard, and but you can clearly see here, right? I mean, I didn't draw it properly, but you can clearly see that this error is here is okay. The whatever the error is, it is very minimal here, right? The error is not that much. So even though we are not able to find the integral exactly, at some point you can just estimate the integral, and most of your computation, let's say whether you want to do the turbulence or whether you want to shoot a rocket, more or less it may be enough, provided you find it with enough approximation, like enough decimal points. If you find it, it more or less enough. You don't need exactly. So most of the time this will be very useful. Okay, anyway, we will do how this rule came, we will do tomorrow, and I was not able to do any examples. Sorry about that. I think we can probably do some example also in the next class, but you might have something in the assignment. So yeah, at least remember the rule and you can try to. Okay, and I will probably stop now. Okay, you want to see the mail here, or I can type it here also if you want. So yeah, in just in case if you have some doubts with that, you can leave me a mail. I will respond to it. Okay, we will end the class now. Next class we will do. We will start with explaining this rule. See, I had uh, taken the notes here. See here, I have taken the notes, etc. But unfortunately, I was not able to do it. But anyway, next class we will do it. Okay, then we will end the class and we will meet in the next class. See you. Yeah, okay, we will